All right, at this point, we have looked at an example of a hyperbola whose branches are opening horizontally, meaning to the right and to the left. We've seen that the equation for such a hyperbola is x squared over a squared minus y squared over b squared equals 1. And if we switch the order of the terms, starting with y squared over a squared minus x squared over b squared equals 1, if we start off with the y squared term that's positive and the x squared term that's being subtracted, what we end up with is a hyperbola that opens vertically, meaning one of the branches is opening upward and the other branch is opening downward. We switch the a and the b, we're always going to have the a squared under the term that's positive, and what that does for us is it makes sure that the vertices always have a coordinate of a. So we have basically the same image that we have before, but rotated 90 degrees so that we're opening vertically instead of horizontally. Now there's just a little bit more I want to talk about regarding these, and then in the next lesson we're actually going to go through and sketch the graphs of some hyperbolas, given equations with actual numbers for a and b. But I want to talk about two pieces. One of them is the asymptotes. So hyperbolas are going to have asymptotes at y equals plus or minus b over a times x, or y equals plus or minus a over b times x, depending on the situation, whether it's a horizontal opening hyperbola or a vertically opening hyperbola. And I want to show you why that's going to end up being the case. And we're going to focus on the first type of hyperbola just to make things easier. So if we take this equation that we have, x squared over a squared minus y squared over b squared equals 1, and we try to solve this for y, we get y alone. I'm not going to go through all of the calculations right now, not all of the algebra, because that's something that you can do on your own. But if we solve this for y, we end up with y equals plus or minus b over a times the square root of x squared minus a squared. The reason we've got a plus or minus is because when you've got a y squared and you solve to get the y alone, you take the square root of both sides, and the square root property gives you a plus or minus. But what we're going to do is we're going to go even further, and we're going to factor out an x from the inside of this square root, and we're going to pull it out. I know the a squared doesn't have an x, but we can divide it by x squared, which is the equivalent of pulling it out. So this is equivalent to y equals plus or minus b over a times x times the square root of 1 minus a squared over x squared. This is an equivalent way of writing that equation. And we notice that if we look at what happens here as x gets larger and larger and larger, as x goes towards positive infinity or as x goes towards negative infinity, because a is a constant, this fraction is going to get closer and closer to 0. A fraction with a constant in the numerator and the denominator getting bigger and bigger and bigger going towards infinity is going to get closer and closer to 0. And so we're basically going to have 1 minus 0, which is 1, and the square root of 1 is 1. And so as x approaches plus or minus infinity, we know that this square root is going to get closer and closer to 1. And so what that means is that y is going to be getting closer and closer to plus or minus b over a times x. So y approaches plus or minus b over a times x. And so what this means is that we're getting closer and closer to this, and we know that y equals b over a times x is a diagonal line, the same if we have negative b over a. And so what this means is that the points on our curve are going to be getting closer and closer to a diagonal line, which is going to end up being our slant asymptote. And we're going to have two of them. We're going to have b over a times x, and we're going to have the opposite of b over a times x. And if we have a hyperbola that's opening in the other direction, it's going to be just a little bit different. It's going to be a over b times x, and the opposite of a over b times x. And the reason is because we've switched the a and the b for being below the x and the y, respectively. So I know that this is a lot to take in all at once, but what we're going to do is we're going to get practice slowly, one problem at a time, looking at these graphs and sketching these graphs in the next lesson. So we're going to take things one step at a time. The last thing I want to talk about is the relationship between the vertices, the foci, and the numbers a, b, and c. So we had a relationship between a, b, and c when we were dealing with ellipses, and we're going to have a different relationship between a, b, and c when we're dealing with hyperbolas, because hyperbolas are very different from ellipses. And so we know that c is involved with the foci, and we know that a is involved with the vertices. So we have this b out here, and b is particularly useful when we're going to sketch these hyperbolas. So in general, one of the things that we need to do when we're sketching the hyperbolas is we need to sketch the asymptotes, because we're going to want to make sure that our graphs are getting closer and closer to those asymptotes. And so the way that we're going to do that is by plotting the vertices, which are at plus or minus a comma 0, or in the other orientation, 0 comma plus or minus a. And then on the other axis, we're going to plot the points b and negative b. And then we're going to draw a rectangle, which is called the central box, because it's in the center of the two branches of the hyperbola. And when we draw this central box, the asymptotes are going to go through the diagonals of that rectangle. So this relationship between a, b, and c is particularly useful for finding the asymptotes, which we're going to need to help us sketch the graphs of hyperbolas. We're going to get into that in detail in the next lesson, but I just wanted to have a quick look at it now so that it's a little bit easier when we need to apply it in the next lesson.